Use the table below, which is from a study on vitamin C intake and the common cold, to test if vitamin C intake and colds are independent. Okay, so this phrase here implies that we're doing a hypothesis test, and of course we're testing to see if these two categories are independent. So it's a chi-squared test for independence. Look at the layout of the data, it's clear that it's a chi-squared test for independence. The procedure then is going to require us to create the claim, the HO, the HA, so on and so forth. So let's go ahead and do that now. For the claim, we're going to say that the two categories are independent, just like it said in the problem. So we'll say claim colds and vitamin C intake are independent. So the idea is that one has no effect on the other. That's what they asked us to test. Now, HO, of course, always is the claim of independent categories, so we're just going to write independent here. And for HA, we're going to say dependent, which is the opposite of independent, right? Okay, so there's our claim, our HO, or an HA. And remember, this HO and HA never changes. It's the same for all the problems. The claim can be either HO or HA, but basically it's talking about independence or dependence in each case. All right, now the next step is the hard step, the step where we have to process all the data. It's really just time-consuming mainly. So let's start with the observations. Now, we only have 4 cells that involve observed values, right? 1, 2, 3, 4. All the rest of these are just totals. So let's write down the 4 totals here. So the 4 cells here, 21, 11, 36, and 35. Now from there you want to write down the expected values for the table. The expected values come from that formula that we have, which is basically when it's a chi-squared test for independence, remember it's row total times column total divided by the grand total. So for our first value here, 21, we want to find the number in the row total, the number in the column total, and then the grand total. So it's going to be 32 times 57 over 103. So we'll put that in our calculators and see what we get. 32 times 57 divided by 103. When you do that, you get 17.709. 17.709. Okay, now for 11, we'll do the same thing. It'll be 32 and 46. So 32 times 46 divided by the grand total of 103. So you get 14.291. 14.291. All right, then for 36, we'll do the same thing. The row total, 71, times the column total, 57, divided by 103, the grand total. 39.291. All right, and then finally last is the 35. The 35 is 71 times 46, 71 times 46, divided by 103. And we get the answer 31.709. 31.709. Okay, now remember the pattern that occurs for observed minus expected during these chi-squared tests for independence. If you subtract these two numbers, that first pair will give you the differences you're going to find for all of them, except for the sign may be different, right? So in other words, we can do 21 minus 17.709. And when we do that, we're going to get this 3.291 difference. Now that 3.291 difference, you will see is going to be constant throughout, except for in some cases it'll be negative, like this case, right? Why is it negative? The 14 is bigger than the 11, so it'll be negative 3.291. Sure enough, if you add that to 11, you get 14.291. So you see that it is that correct difference. And then from there, we'll do 36 minus 39. That'll give you minus 3.291. Again, the 39 is bigger than 36, so it becomes negative. And then 35 minus 31, you get positive 3.291. And of course, you notice the sum here is 0, which is what is supposed to happen as well. Okay, so we have observed, expected, observed minus expected, and then we're going to have observed minus expected quantity squared. So we're going to square all these values, and of course then the negatives won't matter anymore, right? So 3.291 squared, if we square that number in our calculator, we get 10.831. 10.831. So 10.831. And we'll do that all the way down because it'll be the same answer when we square all of those values. Okay, now, once we have that, we have our ever most important column, which is observed minus expected squared divided by expected. And this is going to give us the column that we'll get our test stat from by summing the column at the end. So we have this quantity here that's always the same, it looks like, right? Divided by the expectations, which are all different. So what I want to do is take that 10.831, I want to store it in my calculator as variable x. So I store it in there, and then what I'm going to do is every time I want to do 10.831 divided by something, I'll do x divided by that something. So it'll be 17.709 in the first one. I get 0.612 if I go to 3 decimal places. 0.612. Okay, let's do it again. We'll do the 10.831 divided by 14.291. Get the answer 0.758. 0.758. So 0.758. Okay, then we're going to do the same thing. 10.831 divided by 39.291. And I get 0.276. So very small numbers here, right? 0.276. So these aren't getting very large, and of course we're going to have to add them up at the end, and so our test stat's probably not going to be very large. All right, let's finish up our last one. We're going to do 10.831 divided by 31.709. When we're done, we get 0.342. 0.342. All right, now the sum of this column is our chi-squared test statistic. So let's go ahead and do that. Let's add up those numbers. So 0.612 plus 0.758 plus 0.276 plus 0.342. If you add all that together, you get the answer 1.988. 1.988. This is your chi-squared test statistic. All right, so now that we have our test stat, our next step is to go get our critical value and compare our test stat against it. So let's go now to our a new sheet of paper and draw our rejection region. So let's take a look at our rejection region now. So the rejection region is going to be on the right-hand side of the curve here. And what we're looking for is the chi-squared critical value. We want to know where does the rejection region begin on this number line down here. Now, the alpha for the problem is going to be 5% because they didn't actually mention an alpha, so we'll choose 5% by default. And if you remember, the degrees of freedom are going to be the row number minus 1, so how many rows there are minus 1, the column number minus 1, or how many columns there are minus 1. For us, that's going to be 1 here because this is a 2 by 2 table, 2 by 2, right? We don't include the total columns, right? Just the original data. So there were 2 rows, 2 columns, 2 minus 1 is 1, 2 minus 1 is 1, 1 times 1 is 1. All right, so let's go to our table now and look up this value to see what it turns out to be. Okay, so I'm on the chi-squared table looking at 0.05 with 1 degrees of freedom. 0.05, 1 degrees of freedom, we get the answer 3.84146. Okay, so our critical value turns out to be 3.841, right? 3.841. All right, now that critical value, when compared against our chi-squared test statistic, which we had earlier, it turned out to be, if you remember, 1.988. When we compare the two, it's clear that 1.988 is in the do not reject region. So we're over here somewhere, right, in the white space. So we're going to conclude that we do not reject HO. Do not reject HO, and as a result, we do not support HA. Okay, our original claim is actually the same as HO, so we're going to use that wording for the problem, right? When we look at our claim, it says independent, that's what HO says. So when we say do not reject HO, we'll say the sample data does not allow us to reject the claim, right? The sample data does not allow us to reject the claim. The claim is that vitamin C and frequency of colds are independent. So what it's saying is that essentially this data doesn't provide evidence that taking vitamin C will reduce the frequency of colds.